good morning, everybody, and welcome to this webinar session that is called Powder Atomization and Post-Heat Treatment for Additive Manufacturing. This webinar is within the project ADDITOOL, which is a European Interreg Sudoe project. Well, my name is Miren Aristizabal. I'm a researcher in CEIT, in the group of Advanced Manufacturing in Powder Metallurgy and Laser group. And I'm involved in this ADDITOOL project, and today I will be giving the talk in the second part of the webinar. But first, my colleague, Professor Alejo Abello, will introduce a talk about powder atomization for additive manufacturing. Just before starting, I just let you know that we are going to give several minutes at the end of the two talks in order to answer any question that you have, and that you can use the chat of this webinar to write your questions within we are talking, so we can read them at the end. So please, Alejo, whenever you want, the screen is yours.
Thank you, Miren. I hope that you can hear me well.
Yes.
So my talk is entitled Powder Atomization for Additive Manufacturing. And this is the outline of the presentation. I have divided it into 4 sections: powder production methods, a general overview, then atomization methods for metal powders, the 3rd section, particle size distribution and yield, and 4th, powder characterization. So I'll try to give you a general overview on how powders are produced, and specifically for additive manufacturing, and what are the alternative production methods that you could use. Let's start with powder production methods overview. First of all, if you want to make powder, you have to be aware that there's a number of methods that you could use. Basically, there are 3 main principles which are used to produce powders industrially: chemical, mechanical, and atomization. Let's start with the first 2. In the chemical principle, you use either decomposition of a gaseous compound, for instance, in the well-known carbonyl method to produce fine powders of iron and nickel, for instance. You can also use chemical decomposition from solution, for instance, to produce silver, or electrolytic deposition from solution to produce very pure electrolytic elements like copper and iron. And you can also use reduction of oxide, starting from sponge to produce iron or titanium. And this is a kind of powder you obtain. On the right-hand side, you can see that using reduction, you obtain this sort of agglomerates of a quite large size. If you use the electrolytic method, then you obtain flakes in the case of iron, or some sort of dendritic structures in the case of copper. And if you use the carbonyl method, you obtain very fine particles with a kind of folded structure, or even agglomerates of very fine spherical powders. In all cases, you see that the shape is not spherical, and so flowability of these powders is not very good. In atomization, there are 3 possible ways to fluid using gas or water. In the case of gas, you obtain very spherical powders like this one, and this is why gas atomization is the preferred method to produce powders for additive manufacturing. In water atomization, you obtain also very fine powders, but with irregular shapes. And there are 2 other methods that I will explain later on: centrifugal and ultrasonic and vibrating orifice, which are also very effective to produce spherical powders, but have a lower productivity. Let's move to the second section, atomization methods for metal powders. First, I want to tell something about atomizer configurations. In gas atomization, can be used for almost any metal. It accounts for about half of the atomized powders. You can make spherical powders, usually, and it can be industrially scaled up to about 3 tons per hour. You have a limit in the maximum particle size. So if you want to produce shot, for instance, you're limited by the chamber's height to below 500 microns. And also you have trouble producing very, very fine powders below 10 microns. This is the typical gas atomizer structure. There is a melt chamber with a furnace where you melt and you pour the liquid. It goes through a nozzle. There is a gas, a pressurized gas coming in. It produces a spray. Droplets fall, solidify, and are collected at the bottom. Fine powders are usually collected on a side or even at the bottom also, and separated using a cyclone, and you have another collector here. And as you can see, gas atomization plants can range from small size for lab scale or for very large size for industry scale. In the case of water atomization, the structure is basically the same, except that you use high pressure water to produce the spray. And what you collect at the bottom is powder and water. So this is very compact. It's very productive. It accounts for about half of the atomized powders. It's very cheap because there's lower energy in compressing and pumping water as compared to gas, but you also need to dewater and dry. Water atomization plants are much more compact than gas atomization. To give you an idea, this is the ADDITOOL research atomizer, our own lab scale atomizer. This is what it looks like. We have the melt chamber here for melting about 3 kilograms of metal. You have the atomization chamber, which is quite small in this case. We have a cyclone here and a collector at the bottom. We have a vacuum pump and the induction power source. In centrifugal atomization, what you do is you pour liquid metal on top of a rotating disc or cup, and the liquid forms a very thin sheet by centrifugal force, which at the edge becomes ligaments that break up into droplets, which are quite similar from one from the other. And that is why this method produces a very low spread of particles. There's another method in which it is the electrode itself that it's rotating, and then melting is produced by plasma in what is called the prep method. As I said, it produces very narrow powder size distribution, but to produce fine powder, you need to use extreme speeds in excess of 50, 60,000 RPM. So it's quite limited to some specific applications like those mentioned on the slide. Centrifugal atomization plants are rather compact, and they need to be need to have a quite large diameter to let the particles solidify before they hit the wall. And there are 2 other means which are interesting to know. Plasma atomization, it's a relatively new technique. You feed a wire and then you melt it using plasma torches. Then the spray is produced by the plasma energy. So there's no gas or water involved here. And you can produce, well, any metal that can be formed into a wire feedstock. So availability of the feedstock is what limits the application of this method. And there's also another very interesting technique, which is plasma spheroidization, which converts powders into highly spherical powder. So let's say you have a raw material that is irregular powder. You can force it into a tube, through a tube, and then it joins with a plasma torch. It melts, and irregular particles become spherical, and they are collected at the bottom. So this can be used for these applications, high melting temperature, or even for reconditioning of metal powders that have been used before for AM in an AM machine. So you're reusing these powders. And finally, you have ultrasonic atomization, which produces spherical particles with very low spread. Although it has low productivity, there are some equipments that can be used for lab scale and which are useful to produce small batches. You feed a wire, you melt using a plasma arc, and then a molten metal drops on top of a sonotrode, which is a vibrating plate, which is actuated by normally by the piezoelectric actuator. So the process produces some sort of wave on top of the liquid, and then particles jump from the sheet of liquid and are collected by a cross flow that drives them to a collector. And the powder you get is very, very spherical, free of satellites, and also with low spread. But unfortunately, it has very low productivity. Atomizers use a number of techniques to melt to produce liquid metal. And this is a picture taken from a leading atomization equipment producer. And as you can see, it offers a number of melting process, different melting principles. All of them use vacuum for melting to prevent oxidation. And in the last moment, just before atomization, the melting chamber is filled with inert gas. And there are basically two main options. What is called VIGA, vacuum induction melting, in which you use induction melting in the furnace to melt the powder. You can have raw material with any arbitrary shape and composition, so you can melt here any chemical composition that you wish, just by putting inside the appropriate amount of material with exact composition. And you can use either a tilt and pour mechanism, in which you pour the liquid to a tun dish and it goes to the atomization chamber, or a bottom pouring, in which a stopper rod controls the flow of liquid. Each method has pros and cons. But these methods have serious issues when you try to atomize very reactive metals. And in those cases, you usually prefer ceramic-free method, which are the other four. I will not describe them in detail. Electron induction melting, or EIGE, uses a rod, which is melted using an induction coil. Then the liquid drops and is atomized at the bottom. The shortcoming is that it needs prealloyed rods as raw material. So you need to have prealloyed material to use this method. And there are three others which are very specific: plasma melting induction guiding. In this case, you use plasma, and then you collect the liquid in a sort of water-cooled copper tun dish, which is also heated by induction heating. So it's very, very specific. And it's also crucible-free. Electroslag remelting with also cold wall induction guiding, exactly a similar principle than the previous one, but in this case the rod is melted in contact with a refining slag, which is a method used for to obtain very pure, very clean compositions. And finally, you have also cold crucible, which is a specific type of crucible made of copper, water-cooled, which is surrounded by induction coil. So you heat, and the molten metal creates a skull in contact with the copper, so there is no contamination of the metal because it doesn't even touch the copper, and it's used for very reactive metals, but it's very hard to implement and to operate. Regarding nozzle types, there are two main methods. What is called free fall atomizers, in which the liquid falls freely until it meets the gas. There is about 10-15 centimeters height before the spray happens. It is a very robust method, but it tends to produce coarser powders. And if you want to produce fine powders, usually closed coupled is the preferred method. And in this case, what you do is you use a guide tube that takes the melt closer to the exit of the gas. And it is much more efficient in producing finer powders, but it has a tendency to freeze because the gas here is a very low temperature. So the melt may solidify here, and the process can be interrupted. It usually produces finer particle sizes. Also, nozzles can be convergent or convergent divergent. The difference is in the shape of the nozzle. In this case, you obtain here high pressure sonic velocity. Expansion of the gas takes place here. There's also shock waves being produced here, and well, you produce a spray here. If you want to obtain supersonic velocities inside the nozzle, you need to go to convergent divergent nozzles like this one. There's a convergent part and a divergent one. And here, supersonic, there is a supersonic flow of about 2 or 3 Mach. And they tend to be also more efficient. Theoretically, you could avoid shock waves, which is not an efficient way of using the pressure energy of the gas. But there are both atomizers, convergent and convergent divergent, work well. I want to say something about the influence of process parameters on powder characteristics. If you have an atomizer, there are a number of decisions you can make to produce powder. First of all, you can choose the type of gas you use. Usually you use inert gases like argon or nitrogen, and in some cases you even use helium, which is very expensive. You can choose the temperature. You can preheat the gas or use room temperature. And the main variable is you can choose atomization pressure. You can also choose the diameter of the melt delivered tube, which determines the amount of melt that goes down. You can choose the melt superheating, how high can you go in temperature over the melting point, and overpressure, what is the pressure that you can put here when you fill it with inert gas. Now, let's look at how the atomization pressure influences the production of powder. First, we define GMR, which is a very, very important variable in gas atomization, which is the ratio, gas to melt mass flow ratio. It's the flow of gas divided by the flow of metal. And this is how it changes. Increasing the gas pressure increases GMR, and higher GMR produces finer powder. This is the golden rule of atomization. Higher GMR produces finer powder. This plot shows very clearly how as you increase GMR, D50, which is the median particle size, goes down. Unfortunately, GMR cannot be easily fixed because there is a complex dependency of the melt flow with respect to the gas flow and other variables, so it's not direct. And also, this is not a process that can go forever, because when you use high GMR values, sometimes you obtain solidification of the melt stream and interruption of the atomization process. So atomization pressure increases GMR, which reduces D50. That's the main conclusion. Also, overpressure, you can choose this when you fill the chamber with inert gas. You can have a certain overpressure here to push the melt down. So what we have carried out several experiments with 4 gas pressures and 2 overpressures. And this is how it operates. A higher overpressure produces a higher melt flow, which in turn produces lower GMR, which in turn produces higher D50, which is what you can see here. Every pair of dots here corresponds to different overpressures, and higher overpressure is always over lower overpressure because of differences in GMR. Influence of melt superheating. What's the temperature at which you should stop heating this? That is a question that has to be answered. You have to choose some superheating, and we have here some data of atomizations carried out, copper atomizations with exactly same atomization parameters, except 4 different superheats. And we are comparing here 200 Cs against 500 Cs. And as you can see, you can find differences between the 2 powders. Basically, what you can see is there on the right-hand side, you have finer powders, although you also see that there are more agglomerates and satellites. And that is the conclusion, that in the case of copper, you have a slight decline of D50 and D90 as superheat increases, and you also have an increase in satellites and agglomeration. Also, the type of gas, how does it influence the kind of powder you obtain? We have here a number of atomizations, and we compare nitrogen, argon, and helium. And if you compare what the powder size is for similar values of GMR, you can see that, for instance, these dots of helium are way below what we obtained with argon and nitrogen. So helium produces finer powders, and nitrogen is an intermediate, argon the coarsest powders. The conclusion is that the trend is related to gas molecular weight. Lighter gas produces finer powder, and the reason for this is because lighter gases produce higher velocities at the exit of the nozzle, and therefore have a higher capacity to transfer momentum, and therefore to create surface energy. Finally, the influence of material type. As you can see, different metals. In this case, we have plotted atomizations of copper, 316L, tin, iron, and bronze, and we plot them D50 against volume GMR, which is another ratio you can define. And as you can see, tin is clearly below the rest, copper is intermediate, 316L is above, and higher values of density, surface tension, and viscosity lead to coarser powders for same GMR values, which is a quite logical conclusion. Finally, satellites are something which is undesirable because it is in detriment of flowability. And the cause for satellites is the flow inside the atomization chamber. Basically, you have a very high-speed gas going down, and sometimes you have, well, very often, I would say almost always, you have recirculation loops that train the very fine particles to the upper part, and what happens is that there are particle collisions. So basically, smaller particles bump into higher ones, and what happens is they are either absorbed if they're in liquid state, or they can be in the form of splats or bumps or satellite. And this picture illustrates quite well all these. There are satellites, bumps, splats, etc. I will not get into details. I just want to mention that there are formulas to predict median particle diameter. A very well-known formula is called Lubanskas formula, but we believe at Fate that Kishidaka's formula has a much better prediction capacity, and basically based on these parameters like density, viscosity, surface tension, etc., you can predict quite well what the median particle size will be. As you can see, if we plot measured versus calculated, there is a very good correlation, and therefore this formula has a predictive capability. I will not say anymore about this. Particle size distribution and yield. As you know, the spray is usually divided into zones in which primary atomization takes place. This is the dense region where the melt stream becomes sheets and ligaments and then droplets. And the secondary atomization zone is the dispersed region in which droplets break up into smaller droplets. And this is that kind of mechanism that takes place in secondary atomization, when a droplet breaks into smaller droplets. In the end, the powder you collect in the chamber can be described as a log normal probability function, which takes this mathematical formula where x is the particle size. The interesting thing is that this is the cumulative distribution, which has an S shape, which is very typical of particle size distributions, and D50 is the median particle size, which corresponds to the 50% weight of the cumulative density. An important parameter is, of course, in addition to the median particle size, is the standard deviation, which is a measure of the spread of the distribution. For a sigma ln of 1, all particles have identical size. This is not the case. Usually in two-fluid atomized powder, gas or water, sigma ln is in the range of 1.2, which is very good, 2.3, which is normal. So if you are in the range 2.2, 2.3, that's very normal. Centrifugal and ultrasonic have a much lower spread, and vibrating orifice, which is a very specific method of producing particles, is 1.03, but it has a very, very low productivity. The graphical representation of cumulative mass function, for instance, for an example of a median particle size of 33 microns and a sigma of 2, these are very typical results. You can use a linear plot, which is not very common. You can use a log plot for the probability and for the cumulative, which is on the right-hand side with the S shape. But there's also a third option, which I would like to mention, which is a log plot with a Gaussian ordinate axis. You have a log plot on the x-axis, and on the y-axis, instead, as you can see, this is not linear and this is not logarithmic either, but rather it has a Gaussian transformation. And the nice thing about this plot is that the cumulative density function becomes a line, a straight line. And it is best for plotting experimental results because a deviation from the line often unveils problems with the atomization process. This is an actual example of atomization in which you can see the blue line deviates from the gray line, indicating that there is a larger portion of fine powders in the lower region of the plot. So this might be something that needs to be studied in more detail. Regarding the yield of the gas atomization process, it is known that gas atomization has a quite low yield, especially when you aim at short PSD fractions. Like, for instance, if you want to get powder in the range 15 to 63 microns used in laser powder bed fusion, for instance, then the optimum yield is reached when you tune your atomizer to produce a median particle size of 30 microns. But then, if your atomizer, and this is a surface plot that gives you the yield, so it's a theoretical maximum amount of powder in this range for a given sigma ln value, which is a property of your nozzle and your atomizer. If, let's say, for instance, your atomizer has a spread of sigma ln 2, which is good, and you are able to fine-tune your process so that your median is at 30 micron, then your yield will be 70%. So 30% of the powder will not be used. And in it, also a 2.2, which is also quite average, your yield will be 63%. So it's really a quite low yield. And undesired powder fractions must be removed by sieving. What you do is, if you want to keep the 15 to 63 micron fraction, then this is what you desire. There is about 30% or 35% that needs to be removed, and this is done by sieving. This is the most common sieving techniques. First of all, you have the vibratory multi-stage sieve, in which you have a number of meshes, pans with meshes, and it's vibrating, so that you put as atomized powder at the top and you collect fine powder at the bottom, and it's separated. Every pan contains a fraction. Then, but this has very low capacity. You have multi-frequency sieves like this one, in which you can separate two fractions, or at most 3 fractions, using 2 motors and a vibrator and a vibrating element inside. And also you have air classifiers, which are very effective for separating fine fractions, which are very often difficult to sieve. And to finish with my presentation, I want to say something about powder characterization. This is a flow chart we use to characterize powder. First, you obtain atomizer output. You separate whatever particles are over 1 millimeter, which are not considered powder. Then you obtain the rest. And first of all, you do particle size distribution. You can do this by laser diffraction or by sieving and separating in different fractions, like, for instance, these fractions. We also do morphology analysis using dynamic image analysis, if you have a machine that does this, or you can also use the scanning electron microscopy to actually watch and see how what your powder looks like. You do microstructure using X-ray diffraction or differential scanning calorimetry. We also embed the powder in resin. We do metallographic preparation. We polish. We make. We do chemical attack, and we take this to optical microscopy or to scanning electron microscopy. We also do chemical analysis. We look at interstitials, carbon, sulfur, oxygen, nitrogen, or sometimes we also do detailed analysis using ICP. And finally, you want to know what are the bulk properties of your powder, density and flowability, which are important properties like apparent density, tap density, pignometric density, flowability, and angle of repose. There are very established and simple procedures and machines to do these measurements. And there are other proprietary devices that measure complementary properties like flowability, and you have the rheometer, etc. How these properties affect the part properties and the process properties has been thoroughly studied, and I like this picture, which summarizes some of the works which have looked into how powder properties affect bulk powder properties, like, for instance, particle size distribution, composition, moisture, density, etc., how this influences bulk powder behavior, such as tap density, flowability, etc., and how this affects process performance, and how in turn this affects the final part properties. So I will not summarize this because it's almost impossible. There is a huge number of works in this line. And this is my last slide. Here is a number of powder standards for additive manufacturing. There are lots of standards, and this is some of the ones we use. The Metal Powder Industries Federation, which define how to, sample powders, how to measure flow rate, etc. And I leave them here in case they're useful to you. And this is the end of my presentation. Thank you for your attention.
Okay, thank you very much, Alejo. Just for all the assistants, I will remind that all the questions that you might have, we will answer after the second talk, that is my talk as well. But if you want to start writing the questions in the chat, you have it available. I'm gonna now share the second talk. So this second talk is about the need of post-processing for additive manufacturing. And well, in this case, the post-processing, we are talking about heat and heat treatments. So in this talk, first, what I want to do is to show why do we have this need of having post-processing in the AM manufacturing chain. We will see that actually this is due to microstructural issues and different defects that we can find after AM processes. And I would like to show several examples of how hot isostatic pressing or heat and heat treatments can help to achieve finally good mechanical processes, but after the whole chain. So I will start showing what I mean with the AM process chain. So in this case, we are not only talking about the additive manufacturing technologies itself, but we are starting from the powder atomization that Professor Alejo has recently shown a very nice presentation about it. And then finishing in the post-processing step. So the idea is that after all these steps, we have to have a material with good properties and acquiring the requirements for different applications. In terms of powder atomization, as we have seen, it's possible to manufacture powders with tailored properties, for example, for AM. So we can have specific composition designs or even specific powder particle size distributions. As people that works in AM will know, for each AM technology, we will have an optimal powder size distribution. So then, once that we have chosen the correct powder for each technology, we have the different AM technologies. In this presentation, I'm only going to be focused in AM for powders, so I'm not gonna talk about wire deposition, but yes, about two different type of AM processes. So for instance, the ones that are based in fusion, such as direct energy deposition, or the ones that are powder bed fusion, like SLM or EBM, but also AM processes which are not based in fusion, but in sintering, like binder jetting. Although each technology, as you can imagine, has different characteristics and problematic, what we can say in general is that all these technologies will need a post-processing in order to tune the microstructure of the materials and to achieve the requirement properties. In addition, there are nowadays several attempts to try to integrate the hot isostatic press into the process. So we can, for instance, reduce the times of these direct energy deposition or powder bed fusion process parameters, doing them faster and maybe not obtaining the best material. Maybe we have a porosity, but knowing that afterwards, as we are going to use heat, we are going to be able to close these defects and therefore to achieve a sound property material. So as we say, after choosing the powder and the technology, we have to choose the correct post-processing that usually is by hot isostatic pressing and following heat treatments. We will see that here one of the main issues is that most of the heat treatments are optimized for traditional manufacturing methods such as casting or forging, and that we will need to adapt them to AM materials. So why do we have to do this? Well, first of all, because AM materials have its own characteristics. Here I have several examples of different materials and different processes. In the case of fusion-based AM, usually we have problems with structural integrity and also the directional issues. For example, in this example, we are looking for a microstructure of scanchromal, which is an aluminum alloy. And we can observe that after LPBF, we have this melt pool microstructure and that we have directional grain growth parallel to the build direction. In the case of copper chromium zirconium, in this case obtained by electron beam melting, we also have this columnar grain growth parallel to the build direction. This type of microstructures make the material heterogeneous, so we are not going to have the same properties in one direction than in the other one, and this sometimes it can be an issue for the application. On the contrary, for additive manufacturing, which is not based in fusion, for instance, binder jetting, comparing the same material, we observe that microstructure is completely different. In this case, by binder jetting, which is based in sintering, we have equiaxis grains, so more homogeneous microstructure. However, this type of AM process also has its own defect, and usually we are going to need also post-processing. So, talking about the defects, we can say that in AM, basically the defects can be separated in two types. Ones that are directly related with the material itself, and from the other side with AM process problems or by choosing the incorrect process parameters. When we look for the origin of the defects in materials, we have different examples. For instance, one can be directly related with the raw material, with the powder. If the powders are to oxidize, these oxidized powders can affect in the building and showing porosity. In addition, we can observe in this microstructure a gas atomized powder where we have internal spherical porosity. This porosity is related with entrapment of gas that usually is argon gas, that is the one used for atomization. And due to this very spherical shape, is sometimes very difficult to remove after the AM process. So here we have an example for nickel-based superalloy with a very spherical porosity after the deposition by LMD. Another type of defect that we can find in AM materials and that is related to the material itself is the crack formation. This is very typical in nickel-based superalloys with high amount of gamma prime system. In this case, we have an example again for astroloy nickel-based superalloys, but we can find the same, for instance, for CM247 or other nickel-based superalloys of this family. Just to know, well, it's a good point to know if the material is weldable or not, because this is going to give us an answer to know if it's going to be working well in AM or not. So materials that are not weldable usually are very difficult to process by fusion additive manufacturing. Another problem can be with materials that are prone to formation of residual stress. In this case, there is an example for titanium alloys, and we can see that even if we change the AM technology, we will still have problems with residual stresses. In terms of defects that we can find due to the process, some of the examples are the lack of fusion, keyhole formation, or balling up. Lack of fusion appears when we use energy density which is lower than the required to fully melt the material. Therefore, we are going to find very irregular shaped pores that usually are between the different melt pools, and even sometimes, even if in this microstructure we don't see, we can even find powder particles still without melting. So here is an example for Inconel 718 laser powder bed fusion, where we were using very low energy. But if we go to the contrary, so to use too high energy densities, in this case, we have again porosity, but it's a different one. In this case, this is related with the quick vaporization of the material. Some elements can vaporize and produce these spherical holes or pores inside the melting pool. Another example of defects due to bad process parameters or choosing the incorrect process parameters in AM is the balling up. In this case, this phenomenon affects in the surface of these deposited materials. We see these powder particles attached in the surface of the material, and the roughness is very high. So this can make that during the following depositions, we are going to be forming porosity and therefore decreasing the mechanical properties. So if we ask again, why do we need the post-processing in AM? I think that with these examples that I have shown of a microstructure that is directional, with the different defects that we can find, it's clear that we need to do something after the AM to repair this. So the idea is that after the whole process, to obtain microstructures that are more homogeneous, materials with lower residual stress, and the removal of these defects as porosity and cracks. So for that, we have the post-processing. And one of the best solutions is hot isostatic pressing. Hot isostatic pressing is a heat treatment which combines both high isostatic pressure and high temperature. Here you can find, well, the hot isostatic pressing unit that we have in SAID in the laboratory scale, but nowadays there are very big hot isostatic pressing equipment as well for bigger components. And as we will see, there are also some HIP equipments that has a rapid cooling, which will allow to make the heat treatment inside the heap units. So what does it make heap? First of all, what does is close internal porosity and cracks. So here we have an example of a copper chromium zirconium produced by electron beam melting, and we see how the as-built sample has a very big porosity, but after applying the corresponding heap treatment, we are able to close all this porosity. However, it's true that the heap has its own limitations. As the pressure is applied by a gas, it's not possible to close any open porosity or external cracks. In this case, you can observe that this crack in CM247 nickel-based superalloy is still open after the heap, and it's because, of course, if the gas goes in, it's not gonna close anything. Another limitation of the heap, or something that we have to take into account, is that not always the standard heap treatments are the correct ones, and that we have to modify them as a function of the material. In this case, there is an example of titanium alloy. This is a CT scan image where in red we observe the porosity inside the titanium components after the AM, and in the first time we see that after doing the heap we are able to close all the porosity, so we don't see any red spot. However, if we have to tune the microstructure afterwards with heat treatments, that in titanium alloys is very common, as we will see later, there is a problem, and is that if we introduce a heat treatment with a temperature higher than the one that we had in heat, we are gonna reopen this porosity again. And this is known as TIPS, or thermal induced porosity. But there is not only limitation and risk, there is also other advantages in HIP. And as I say at the beginning, now new HIP units come also with or have introduced a rapid cooling in their technology. This is a good option in order to make the heat treatments inside the HIP. And why can this help to us? Well, if we observe the conventional post-processing that usually is being used, there is a first stress relief treatment, then we use the hot isostatic pressing for closing all the porosity and the cracks, but because the heat traditionally cools very slowly, the microstructure that we obtain afterwards is not the optimal. So then we have to do again solution treatments with a quenching, and then a precipitation treatment with again air cooling or quenching. So applying directly the rapid cooling in the heat process, what we can do is make directly the stress relief and the solution treatment in the heap, so we are removing these two steps at the end of the process. Like that, we can have lower lead times, reducing of costs, and make these options suitable for AM technologies. About heat treatments, well, it's true that this is not a new subject. Heat treatments are known for metallic components from centuries. There are a lot of standards for quenching and annealing tempering processes, and each material has its own heat treatment. However, what's the problem in AM? The problem in AM is that the microstructure that we obtain after different AM technologies is not the same as the ones that we have in forging and casting. And all these heat treatment that I have said that there are standards and they are very well known are optimized for casting and forging. Therefore, we don't start from the same initial microstructure. We don't have the same defects, we have different ones. So this means that we are gonna need to adjust these heat treatments for the AM processes. And actually, nowadays there are a lot of studies trying to optimize this heat treatment, and they have to start, or they have been starting making standards for these new technologies. So just some examples for different alloys. of just to understand why the standard heat treatments for casting and forging are not always the most suitable for AM materials. In this case, I will start with a well-known nickel-based superalloy Inconel 18. In this case, we have a LPBF manufacturing process for this alloy. And just to know that this material is strengthened by gamma prime and gamma double prime phases. However, when we manufacture it by LPBF, because of the rapid cooling of this process, we are going to find this dendritic microstructure, which is full of lavage phases, which are detrimental intermetallic phases, which are brittle. And also because we have done this fast cooling, we don't have time to precipitate the gamma prime and gamma double prime. Therefore, the initial AM material doesn't have the correct properties. We have a material with low strength because we don't have gamma prime and gamma double prime, and well, we have a high elongation, but the problem basically here is that we have to increase this strength. So when we do the heat treatments, for instance, the solution treatment, we are able to remove this dendritic microstructure and we start precipitating well, different elements, such in this case we are seeing delta phases and also gamma prime and gamma double prime. However, if we use the standard treatments for forging and casting, in this case in pink we can see the standard for forging, that is solutioning and aging, and in green we can see the standard for casting, that is homogenization, solutioning and aging. First of all, we see that yes, we are able to increase the UTS and to have even similar gel strength comparing with the forged materials. However, the problem is that we decrease completely the elongation of this material using this heat treatment. So it's needed to optimize this heat treatment in order to, although we increase the strength, not to lose as much this elongation. There are other nickel-based superalloys that we say that are not the best option for fusion-based additive manufacturing. One of them is the CM247. Those superalloys tend to crack if we do, for instance, LPBF systems or LMD with fusion. So therefore, binder jetting in this case is a promising AM technology. However, when we do the sintering in AM, even if we optimize this sintering process and we are able to reduce in a high amount the porosity, we have still these defects in the material and it's needed to post-process it. After applying hot isostatic pressing and different heat treatments for CM247, we can see in this example a microstructure very homogeneous and without porosity with good properties. This was a work done by Zeit and Tecnalia, and in this one what it was obtained was to validate the feasibility of binder jetting for this alloy. Changing the type of alloy, well, nickel-based superalloys, they can be for applications such as aeronautic, titanium alloys as well, but here as well we can have other applications such as biomedical applications. But these materials as well, when we are processing by fusion-based additive manufacturing, we obtain a microstructure which is not ideal. In the case of titanium 64 alloy, what we obtain after LPBF is a martensitic phase, alpha prime martensitic phase, which is very brittle and therefore also the fatigue life is very poor for this material. Therefore, we have to heat treat this material. And in this diagram, we see that the temperature range for the decomposition of alpha prime martensite is between 600 and 900 degrees. So we had a project called CEFAM where we were trying to optimize these heat treatments. We use different temperatures, one low temperature, intermediate temperature, and then the standard one that is used for titanium 6-4 in the standard or conventional manufacturing processes. In this case, we observe that with the heat treatment, we are able to transform the alpha prime martensite into alpha plus beta. However, in the low temperatures, we have still some remaining of this AM microstructure. And in the case of a standard treatment and the intermediate treatment, we have the correct microstructure. When looking for the properties, in this case we have fatigue properties, we observe that between the standard without heap or the standard with heap, the best option or the one that has a higher life is the one with heap. In addition, if we compare in purple the standard temperature and in blue the alternative one, we see that we are able to increase this fatigue life by reducing slightly the standard temperature in titanium 6-4 alloys. So again, we see that sometimes the standard treatments for the conventional manufacturing methods are not the best option in our case for AM. In this titanium 6-4, there is another risk that can be also due to the post-processing, which is the formation of alpha case. This alpha case is an oxygen-enriched surface phase produced when the titanium alloys are exposed to a hot air or oxygen. The problem of this phase is that it's brittle and it can initiate the cracks, so it reduces the fatigue life. And the solution for this is to try to control the atmosphere during the heat treatments. So we have to be sure that the atmosphere that we are using is low in oxygen, but even if we are able to reduce this alpha case formation, sometimes we are still needing sandblasting or machining for the surface finish in order to remove it and to obtain the higher mechanical properties. And just to finish, some examples for other materials such as steels. Here we have two examples. We have the 316 stainless steel and the 17.4 pH. And in both, I'm not going to go in detail of these studies, but just to see that when we are having microstructure directly from AM process, we have a dendritic microstructure, which is not the optimal because has a poor mechanical properties, and that we need to find a post-heat treatment that are able to remove this type of microstructure and achieve the correct grain growth and the correct precipitation in order to have a good mechanical properties. So as conclusion, well, it's clear that we are going to need always post-processing, sometimes with heat, sometimes just heat treatment, but we are going to need to post-process it in order to achieve the requirements of different applications, and that each material is going to need its own heat treatment. The problem that we have seen is that at the moment, most of the HIP and heat treatments are optimized for forging and casting. So we need to adapt them for AM treatments and try to standardize them. And finally, that there is nowadays an option to integrate the HIP in the whole AM value chain in order to be sure that we are going to have finally a correct properties, and that this is feasible nowadays industrially because the new HIP units actually has a rapid cooling that allows to make the heat treatment directly inside the HIP. So this has been everything from my side. I don't know if there are any questions. Okay, so anyway, I think there is no questions. We can finish. Thank you very much, everybody, for attending this webinar.
Thank you, Mire. Bye.
Bye-bye.